Welcome to Water and Wastewater Treatment Engineering. This is Module 2, Water Treatment. In this module, we will be covering the calculation of water demand and talking about water supply sources. We're going to cover the topic of coagulation and flocculation for the design of water treatment systems, settling theory and sedimentation tanks for water treatment systems, granular media and membrane filtration, chemical disinfection, water storage and distribution, and also some treatment processes used in small flow systems such as softening and ion exchange. Demand and supply. In this part of the module, our learning objectives are to describe the extent and the different types of water use activities in California and in other regions. To understand the types of water resources that are available in California, as well as the agencies and the authorities that manage them. To calculate the maximum daily and peak hourly demands for water, as well as the needed fire flow for design purposes. And to calculate well production discharge rates for confined and unconfined aquifers. So this is a map that's showing the extent of environmental stress due to the alteration of flow regimes throughout the world. And by alteration of flow regimes, what I mean really is to what extent are rivers and streams diverted from their natural occurring pathways for use in systems that are serving human uses like irrigation or water consumption, etc. So what you can take away from this graph, you can see here that in the United States, and in particular in the southern and southwestern United States, the flow regimes have been severely deviated from their natural courses. And so there is a good amount of environmental stress that's been caused by that. So California in general has been described as one of the states that has perhaps the most alterations in the natural water systems, as well as a region that experiences moderate to high physical water scarcity, as you can see in this next plot, which shows regions of the world that have different levels of water scarcity. So again, you see the southern, southwestern United States in particular that fit into that category. So who uses water? The water that we withdraw from surface water or from groundwater sources, what is it being used for? We've got some categories here that are throughout the world globally. This is the predicted global water demand by sector up until 2040. So you can see primary energy production, which is a major use of water. Power generation is also a major use of water withdrawals. Industry, municipal water being, of course, the water that we use at the household level and for small businesses, etc., in urban settings and in small towns. But then by far, the use category that demands the most water globally is agriculture, that you can see here shown in the green. So agriculture consumes up to 80% or so of the water withdrawn throughout the world. And one thing you can also take away from these graphs is that the water withdrawal and the water consumption is increasing from year to year. As you can see, the increases between 2014 and the projections to 2025 and 2040. So we use water for a variety of purposes. In the US, the data are somewhat similar to the global data. So we have a little bit more water withdrawals for thermoelectric power. As you can see, 45% of US freshwater withdrawals are used for thermoelectric power. But we use quite a bit for irrigation, 32%, smaller amount for public supply, 12%, and then some other uses which are less common. Water use at the domestic level varies throughout the United States as well. So in some states, the domestic water use per person is much higher than it is in other states. And here you can see that, in particular, some of the western states, including Nevada, Utah, Idaho, Arizona, you see that not only is the domestic water use higher than it is in other regions of the country, but the population growth is also higher in some of these states, 32, 33%, even higher in Nevada. California is a little bit less than some of those other western states, although we do have domestic water use somewhere in the middle compared to other states in the country, and pretty significant growth rate as well. So it's important because you can see the western and southwestern states in the U.S. not only use more water per capita, but it's the location where the highest rate of population growth is occurring. They also happen to be those regions that you saw in previous maps that are the most water scarce, where water bodies have been diverted from their natural courses. And so water management in general in the southwestern United States is a very important task, and can become a very challenging task in some settings. So let's look at California in a little bit more detailed view here. We can see that in Northern California, a good percentage of the water use is dedicated to environmental purposes. So that means, like maintaining biodiversity in streams and maintaining base flows for environmental protection. And this is partially a result of the fact that the north part of California has much more water resources than Southern California and then some of the inland counties. So that environmental use of the water becomes more important in those settings, although it's important, of course, everywhere, just that in the Northern California there's more quantity to go around. For agriculture, you can see definite differences between the Central Valley, some of the inland counties compared to the coastal counties in California, where less water is used for agriculture along the coast and much more is used for agriculture inland. And then urban water use, if you see the south coast where San Diego County is located, that is definitely the dominant use of water in Southern California. So these demands for water and what water is used for varies dramatically, not only from country to country or from state to state, but even within a single state like California varies from region to region. And it also varies from season to season. So in the wet years, much more of the water is dedicated to environmental protection, and in dry years, much more percentage-wise is dedicated to uses like agriculture and urban water supply. So when we design water treatment and distribution systems, the place where we need to start is to calculate how much demand there is. We need to know how much water is needed. All right, so water demands, like I said, it varies region to region, but within a city, the water demand also varies based on the use category of the land. So we've got zoning maps that can help us determine what the current and some of the projected future use categories are for properties within a city. And here you can see a screenshot of the zoning map for a region of San Diego along, I believe that's El Cajon Boulevard. So based on these use categories, the engineer will develop present and future land use maps for the service area that define use categories using some of these descriptions. For example, residential zones, which you can see in the yellow, and there's several different types of residential zones that have different density requirements in most zoning maps. You'll also have districts that are designated as business districts, commercial or institutional districts, park spaces, hospitals, hotels, industrial uses, offices, and schools. So the first step is to define the service area and then look at the different land use types within that service area and calculate how many acres are dedicated to each of these different land use categories. And this is all defined in the City of San Diego Water Department design guidelines, which you can see the Chapter 2 of those guidelines governs how to calculate water demands and service criteria. So you can find all of these guidelines from resources like that. All right, so once we define the land use categories within our service area, the next thing we want to do is determine the total equivalent population for any residential zone, or determine the total acreage for other uses, and then multiply those values by the water demands that are listed in the design guidelines. So you can see here the table 2.2 on the right. This comes from the City of San Diego design guidelines. You can see for any land use category that's designated as residential zone, the unit water demand that should be used for design purposes is 150 gallons per person per day. For other districts, you can see like central business district, hospitals, industrial uses, etc. There are different unit water demands to use for design purposes, and those are based on square footage or acreage of those facilities. So using this process, we can come up with a total volume per unit time that is required for design of water treatment systems. So you'll express that typically with the units of million gallons per day. That would be considered the average annual demand of water for the service area. From that average annual demand, however, it's going to vary, like we talked about before, seasonally from wet season to dry season, and it'll even vary throughout the day. So during waking hours, of course, there's much higher demand of water, and during the nighttime hours when most people are sleeping, there's a much lower demand. So once we get the average annual water demand using the approach described in the table on the right, we would then apply hourly and maximum daily peaking factors to calculate the hourly peak flow required as well as the maximum daily flow needed. And this will help us determine our storage requirements for water so that we can store water in tanks and reservoirs during periods of low demand, and then draw down those reservoirs, draw down the level in those tanks during periods of high demand. So here's a figure that comes again from the City of San Diego Water Treatment System Design Guidelines, showing how to calculate the peak hour demand factor based on the average annual demand and the region within the city, the neighborhood within the city that the system is serving. So let's say we had an average annual demand of 10 million gallons per day. We can look up from the x-axis at the number 10, move up until we hit the line corresponding with the neighborhood that the system is serving. So if it's an inland central neighborhood, we would look at the dashed line there, which corresponds to a peak factor of approximately 2.6. So that's the ratio of the peak hourly demand to the average annual demand. So that's how we would get our peaking factor for the City of San Diego. And here's a similar chart that you can see for the maximum daily demand. So just like we did for the maximum hourly demand, we would use the same process, take the average annual demand, which let's say we have a value of 10 million gallons per day, and move up until we get to our neighborhood that we're designing the system for. So if it's inland central, again, that would correspond to approximately 1.5 or 1.4 or so, peaking factor of 1.5, 1.4. So if the average demand is 10 million gallons per day, the maximum daily demand would be equal to let's say 1.5 times 10, which is equal to 15 million gallons per day as a maximum daily demand. Let's do an example problem. So using the approach described previously and the table shown on the right, let's assume that we are designing a water system to serve a region in coastal downtown San Diego that includes the following land uses: 3 acres of R2 residential, 15 acres of R3, 18 acres of R4 zone. Let's say there's a 20-acre landscaped park, 4 acres of hotels, 10 acres of schools, 5 acres of office spaces, and 3 acres of a central business district. So using this information, calculate the maximum daily and the hourly peak water demand. Alright, so for this example, we're looking for the maximum daily and the peak hourly flow required to meet the demand in a particular service area. And our service area includes the following land uses. Alright, now for the residential districts, we've got population densities that are assumed for each district. So, for example, in R2 zone, we have 45 people per acre. So, really here we would want to calculate the number of people present in that zone. So we've got 3 acres with 45 people. That's 135 population equivalent. We would do the same thing for the R3 and the R4 zones and find that here we have 1,680 people and 3,528 people. For the rest of the land uses, our water demand is based on the acreage, so we can just leave it at 20 acres, 4 acres, 10 acres, 5, and 3 acres. So now we want to input the gallons per day required per unit. And for the residential zones, the unit is per person, but for the rest of the zones, the unit is per acre. So those requirements are listed in the table that comes from the design manual. So for zone R2, our gallons, zone R2, R3, and R4, the gallons per day is 150 gallons per person per day. For the park, the value is 4,000. For the hotel, 6,555. For the schools, 4,680. For office spaces, we use a value of 5,730. And for the central business district, 6,000. The last step here is to multiply these unit values by the units and come up with the total number of gallons per day. So I'm going to erase to have some more space here. So we have 135 multiplied by 150. And that's equal to 20,250 gallons per day. We'll do the same calculation for all the rest of them and get the following values. Note for this land use, which is a park, 20 acres is our units. Our gallons per day per unit is 4,000 gallons per day per acre. So we just multiply the 4,000 by 20 and that gives us 80,000. Same goes for the rest of these uses. Alright, the last step then is add up all of these values, and if we add up all those values we get approximately 1,000,000. We can round that to about 1 million gallons per day. So that would be our annual average demand of water for this particular service area, 1 million gallons per day. Alright, so you can see from our calculations that we found that the average annual demand for the service area described was approximately 1 million gallon per day. So using the charts shown in the previous slides, we can find the corresponding peak hourly demand for our coastal downtown zone. As you can see on the left, if we look from the x-axis at the value of 1 million gallon per day, we go up until we hit that curve for coastal downtown San Diego, and it corresponds to a peaking factor of approximately 4.2. So our peak hourly demand would be equal to 4.2 times 1 million gallon per day, which is equal to 4.2 million gallons per day. Same process to find the maximum daily demand of water. Based on our average value of 1 million gallons per day, we can find that the corresponding peaking factor for daily maximum demand is 1.8, which would be equivalent to a peak daily demand of 1.8 million gallons per day. So that's part of the flow rate needed for design purposes. The other part of flow rate that is needed for design purposes is to satisfy municipal fire protection requirements. So the needed fire flow, or NFF, is defined as the rate of water flow required for firefighting to confine a major fire to buildings within a block or a group complex. And this is based on the assumption of buildings that do not contain sprinkler systems, or if they do, it's assuming the potential failure of those systems. And the determination of the needed fire flow for a building complex considers elements such as construction of the building, occupancy of the building, exposure, and communication of the building with nearby buildings. So, and these values are typically rounded to the nearest 250 gallons per minute. So again, the first factor used in the calculation of this flow rate is construction. We denote that using the symbol C sub I. The construction factor, which will be expressed in either gallons per minute or liters per second, is calculated using an equation like the one shown up on the screen. So if we're using US units, it would be 18 times F times A sub I raised to the 0.5, where F is a coefficient related to the class of construction. So if it's a wood frame building, we use an F value of 1.5. If it's an ordinary building, F value of 1.0. Buildings that have some kind of fire resistive material for the construction, or even masonry like non-combustible materials, will get a lower coefficient for the F factor. For the A sub I, this would be the effective area in square feet or in square meters of the building. So this is defined as the largest floor in the building plus a percentage of areas in other floors if it's a multi-story building. And there's some guidelines depending on the class 1 through 4. We're going to consider only 50% of all other floors in addition to the largest floor in the building. For building class 5 or 6, it's related to the vertical openings, and we would typically consider 25% of the area not exceeding the 2 largest floors. So these guidelines are written in more detail in the NFPA document, which I will post to Canvas. But this is in general the approach that's used based on the construction and the effective area of the building. The maximum value we would use as well for this purpose would be 800 gallons per minute for classes 1 and 2, or 6,000 gallons per minute for classes 3 through 6, or for a one-story building of any class. And we would never use a value lower than 500 gallons per minute. The second factor that's taken into account to calculate the needed fire flow is occupancy. So occupancy has to do with what types of activities or what types of materials are stored in the building. So if we have materials like marble, stone, or metal products that are considered not to be they're not considered to be an active fuel, if at least 95% of the floor area has these types of materials and there are no C5 class materials present in the building, then we can classify this as a C1 occupancy. For C2, these would be materials that have limited combustibility, like banks, churches, shops, hospitals, motels, offices. They would be construction class 5 or 6. And if it's a mixed-use building, then the requirement is that 80% or more of the floor area should be occupied by C1 or C2 classifications. For C3, these are materials with moderate combustibility. Some examples would be food markets, most wholesale and retail sales uses, as well as service and repair shops. And for C4, these are materials like furniture, wood products, freight depots, terminals, theaters, which contain materials that are freely burning, usually made out of wood or made out of combustible materials. For mixed-use buildings, as long as C5 materials are less than 15% of the floor area, and C4 and C5 materials are less than 25% of the floor area, they would be classified as well as C4. The last category is C5. These are highly combustible materials, so explosives, any building that stores chemicals, paint storage, plastic products, upholstering shops, right? These are all materials that could be considered either highly combustible or may spontaneously ignite. And in a mixed-use building, if C5 materials take up more than 15% of the floor area, the entire building would be considered a C5 occupancy. And you can see, depending on the combustibility class, so C1 through C5, they are given a different occupancy factor, ranging from 0.75 to as high as 1.25. The last two factors that are considered when calculating the needed fire flow are exposure and communication. And so this has to do with, it's related to buildings that are either exposed or they have some type of physical communication where fire can move from one building into another. The factor that's used to calculate that needed fire flow is based on the side of the building with the greatest exposure factor and the greatest communication factor combined. So if the building has 4 sides, we would look at exposure and communication factors for each of those 4 sides and then choose the combined x plus p value that is the highest of the 4 sides. And that's the value that would be used to calculate the needed fire flow. The maximum value for x plus p is 1.6. So it's calculated as 1 plus whatever value we determine for x plus whatever value we determine for p for a given side of the building. And how do we find that x factor? The exposure is related to the construction and the length height value of the exposure building and the distance between facing walls of the subject building and the exposure building. So an exposure building being defined as a building with a wall that is 100 feet or less from a wall of the subject building. So if we have a building that's very close to our building of interest, that would be an exposure building. If that construction wall, if that facing wall, is built using frame, metal, or masonry with some openings, then depending on its distance from the exposed building and the length, height product of the facing wall, we would give it a different exposure factor, x factor, depending also as well on the construction class and the openings. So this is a bit of a complex table, but let's take an example. Let's suppose that the facing wall of the building being evaluated is masonry, and it's located within 20 feet of the exposed building, and the length, height product of the facing wall is equal to 250 foot stories. So then we would be in this group here, the second group below, where you can see that, let's suppose we have the construction of the facing wall of the exposed building is construction class 4, and we have unprotected openings. So looking up the value in the table for all of those inputs, we can find that the exposure factor would be 0.18. Another example, let's suppose we have a metal wall being evaluated, and the distance between that wall and the exposed building is 75 feet. The length height product of the facing wall of the exposed building is 75 feet stories, and the construction class is 6, and the construction of the facing wall is semi-protected, so wire glass or outside open sprinklers. In that case, we can look up the value and find that the X factor should be equal to 0.04. All right, so that's how you can use a table like this. The communication factor is the other piece of that. So if you think about communication of a fire from one building to another, or even within one building, from one room to another, some of the engineered controls that are placed within a building to prevent communication from one room to another are like fire doors that automatically close, and they're fireproof, so they would prevent the flow path of the fire from entering other communicating paths. So this is the same as true if it's a communicating path from one building to another, and that would be how we find the factor for communication. So again, we can use a table like the one shown here to the right. If we're dealing with a communication with a building that's combustible, so like a building that's built with timber, wood construction, and if it is open, so the protection of passageway openings are not enclosed, and those openings are 11 to 20 feet. If our protection of passageway openings is unprotected, we would then have a p-value of 0.20. All right, and if we have a fire-resistive, non-combustible, or slow-burning communications that are enclosed, let's say 11 to 20 feet, and the single class B fire door is present at one end of the passageway, the communication factor would also be 0.20. So this is the way you determine the communication factor. You add up the exposure factor and the communication factor for each of the 4 sides of the building, and whichever one is the maximum is the one that gets used in the equation shown here on the first page. So the needed fire flow is equal to C sub I times O sub I times X plus P sub I, and that's rounded to the nearest 250 gallons per minute, where I is indicating the sides, each of the sides of the building of interest. And now I'll mention in some city codes or design guidelines for water treatment systems, the determination of fire flow requirements is a much simpler process. It might just be looking up the value in a table, but the National Fire Protection Agency, NFPA, developed this formula which can be used to estimate the needed fire flow if it's not specified in design guidelines, or for municipal agencies or water authorities to develop their own guidelines for estimating fire flow. So that would be for the process used for mixed-use buildings, large buildings. For single-family and two-family residential areas, we often would just use a table kind of like the one shown below, where we have the distance between residential units, and based on that distance, how close together each of the residential units are to each other, we would determine the needed fire flow based on that information. So let's do an example. A 2-story wood frame building has a restaurant on the first floor with the following dimensions: 2,250 square feet, a cabinet making shop on the second floor with 900 square feet, 30 by 30. The building has 2 sides with exposures to adjacent buildings. Opposite the long side of the restaurant, at a distance of 11 feet, is building A, which is a 2-story masonry wall construction with semi-protected openings. The length height measurement of that building A is 120 feet per story, so that's 240 foot stories because it's a 2-story building. The second exposure is building B, which has a width of 28 feet at a distance of 12 feet from the end of the restaurant. This building has frame walls with 2 stories for a length-height measurement of 56 foot stories. Again, 28 feet per story, and there's 2-story building. So using that information, calculate the needed fire flow for this restaurant/cabinet shop mixed-use building. Alright, so we have a lot of information presented in this example problem, but what we need to determine are the following 4 factors. What's the construction factor? C. What's the occupancy factor? O. And what are the exposure and communication factors? X plus P. So let's start with construction. What do we know about the construction of this building? Well, we're told it's a wood frame construction, so we know the F value is equal to 1.5. The effective area includes the ground floor plus 50% of the second floor, according to the guidelines. The effective area we should use should be the ground floor square footage, so that is equal to 2,250 square feet plus 50% of the second floor square footage. Second floor square footage is 900 feet, so 50% of that is 450 square feet, which gives a total of 2,700. Alright, so using the equation to calculate the construction factor, we get C is equal to 18 times 1.5 multiplied by the square footage, 2,700, raised to the 0.5 power. And that's equal to 1,400 gallons per minute. All right, next we want to look at O, occupancy. Alright, so in order to determine occupancy using the table provided, we need to take a look at the cabinet making shop and what percentage of the total floor area does it occupy. So the square footage of the cabinet making shop is 900. So if we take 900 and divide it by the total square footage of the building, which is 2,250 plus 900, this equals 28.6%. So that's greater than 25% of the total building square footage. Therefore, based on the table, we're going to use an O factor of 1.15. All right, the last piece to consider here is exposure and communication. All right, so based on what information we're provided, there is no communication between this building and adjacent buildings, so we don't have to worry about the P factor in this case, but we do have some exposure information. So the exposure for building A at a distance of 11 feet and a length height product of 240 feet stories is So again, that's for a distance of 11 feet with a length height product of 240 feet stories. This is for building A. For building B, we've got the building at a distance of 12 feet with a length height product of 56 feet stories. So, according to the table, this exposure factor for building B would be equal to 0.17. So again, that's at a distance of 12 feet. And the length height product is 56 feet stories. Therefore, the building with the largest factor is building B. So for X, we're going to use a value of 0.17. Because we have no communication in this example, P is equal to 0. So the sum of X plus P is equal to 0.17. Or sorry, 1.17. All right, since X plus P is equal to 1.0 plus X plus P. So 1.17, which is the maximum value based on our calculations. All right, so we've got X plus P, we've got O, and we've got our C value. Last step is to put it all together. 1,400 gallons per minute times 1.15 times 1.17 is equal to 1889. But we would typically round that up to the nearest 250 gallons per minute, so we can say approximately 2,000 gallons per minute for fire flow. All right, so let's talk about water rights in California. So we went through the procedure of how to calculate water demands and how to determine how much water is needed for a given service area. But now the next question the Water Authority would have to come up with is where is that water going to come from? Is it going to come from groundwater? Do we have enough available groundwater? Is it going to come from surface water? If so, do we have the rights to use that surface water? In California, especially in Southern California, the availability of water from surface water in particular is very much tied to river rights and historical ownership over the water source. So the river capacity is dictated by the governing agency. The main river supplying water, surface water for Southern California is the Colorado River, which, as you can see in the figure, runs along the border of California and Arizona. And the laws provide the highest priority to the earliest water users. This has been described as the first in time, first in line system. So for example, as an example, the Imperial Irrigation District in Imperial County has earlier water rights than some of the agencies that serve the coastal cities in Southern California. So they would technically get ownership, have higher priority over some of the coastal water users. We have agencies that govern the water use and the water rights for different service areas. So the Metropolitan Water District, MWD, is responsible for the service area shown in yellow here, which includes San Diego County, of course, and we've also got the Coachella Valley Water District and the Imperial Irrigation District, which serve those inland regions of Southern California. Surface water in Southern California, like I mentioned, is highly altered. It's, as I said, been described as the most hydrologically altered landmass on the planet. So surface water in California is transported for hundreds and hundreds of miles to reach its location where it's used, from where it's generated. And sometimes this transportation of water even goes across watershed borders. So California's water supports 35 million people and is used to irrigate more than 5.6 million acres of farmland. California, as you might know, is the leading agricultural producer in the United States. It's a major manufacturing center. It's the most populated state in the United States, and it's alone, if we took the state's economy by itself and compared it to other countries in the world, it would be the 8th largest economy in the world. So all this economical activity has a high demand for water, and in order to supply those demands, supply the amount of water needed for those demands, water is transported from very far away to get to its end use. So we've got here this map showing engineering projects that are were implemented at the federal level, at the state level, state and federal combination, or just local projects as well, where you can see are bringing water from, for example, the Colorado River via the Colorado River Aqueduct over to San Diego service area. So you can see also some federal engineering projects that bring water from the Colorado River over to the Coachella Canal and the All-American Canal, which serves Imperial County. We've also got water coming from the Bay Delta watershed down from Northern California into Southern California and serving the Metropolitan Water District as well. So we get our water here in San Diego from a mixture of different sources, including the Colorado River system as well as the Bay Delta watershed system. A small percentage of our water is also sourced locally from surface water, groundwater, to a very limited extent, and desalination plant. If we break up the Metropolitan Water District's member agencies, so the MWD is the umbrella authority governing all these different member agencies. We can see San Diego County Water Authority down here shown in blue. Of course, we've got separate water district that serves Orange County. We've got the Western Municipal Water District serving inland. We've got Los Angeles Water District, and Las Virgenes Metropolitan Water District. So a lot of different member agencies of the MWD. And you can see here also the locations of some of the treatment plants that are serving these areas. Within the San Diego County Water Authority, so even zooming in a little bit further just to our water district, we've got member agencies of this water authority. And so that includes Carlsbad, MWD, the City of Del Mar, City of Escondido. You can see here on the right all the different service areas for water treatment and distribution systems. And so this is the way that water treatment and water management in Southern California is organized. Like I said, in San Diego County, we've got some local water sources, which are shown here. This is the map of watersheds for San Diego County. So you can see the San Diego River, which is the watershed where San Diego State University falls within that watershed. But we've also got the Sweetwater watershed, the Otay watershed, and the Tijuana River watershed, and including also a small watershed, the Pueblo watershed, which is serving other parts of San Diego. If you've lived in San Diego for some time, you've most likely heard about the Pure Water Project, which is a project that is being implemented right now that will eventually supply approximately 1/3 of San Diego's population with recycled water for potable use. And this has been a project that has been planned for quite some time. and is now at the stage of construction, at least of phase one. However, it's important to mention that while this is a planned wastewater reuse project, San Diego and much of Southern California has been reusing wastewater for potable use for some time now through what's described as de facto wastewater reuse. So because we get our water from the Colorado River, which is a huge river system running through the states of Colorado, Utah, Arizona, into Nevada, as you can see, there's many cities and towns, large urban centers along the river and its tributaries, and each of those cities and towns have their own water and wastewater treatment systems, and many of them discharge treated wastewater back into the Colorado River. So by the time it gets down to the discharge point where it's extracted to be transported over to San Diego, it's already been used and reused by tens, dozens of cities and towns upstream in the watershed. And the same would be true for Northern California water sources that are piped down through the state aqueduct. So this is what we call de facto wastewater reuse, and what the goal of the city of San Diego is through the Pure Water Project is to purposefully implement wastewater reuse systems as a way to control the treatment processes and to be able to have more control over that and rely less on imported water. All right, so the Pure Water San Diego is a phased multi-year program. It's going to eventually provide 1/3 of San Diego with locally supplied water by 2035. It's going to consist of several different phases. Phase one will pull wastewater from the Marina Pump Station and pipe it up to the North City Water Reclamation Plant, which is currently used to produce purple pipe water for irrigation. However, once the phase one of the Pure Water Project goes into effect, some of that tertiary wastewater will get pumped over to a new treatment facility called the North City Pure Water Facility, where it will get treated to essentially drinking water standards and then piped over to the Miramar Reservoir, where it will be stored for a period of time before being extracted and treated again in the Miramar Water Treatment Plant. So I mentioned before, in addition to these surface water and recycled water sources, we also have groundwater in California, although not so much in San Diego County, but in some other Southern California counties like Orange County, groundwater supplies quite a bit of the water demand. So overall, throughout the state, it's responsible for 40 to 60% of California's freshwater needs. It's the main supply for many of the rural areas in California, including some larger cities like Bakersfield and Fresno. 90% of the drinking water along the Central Coast comes from groundwater. And however, it's almost non-existent in some of the major cities, including San Diego and also San Francisco. So in general, in terms of groundwater management in California, there's a need for more managed aquifer recharge systems, so to avoid from overdrawing from aquifers and depleting the reserves that are there. Still, California pumps out up to 2 million acre feet more per year than what goes back into these groundwater aquifers. So currently engaged in a non-sustainable process of groundwater extraction. However, there are some good examples of managed aquifer recharge programs that have had good results in some places in California. So this figure on the right, you can see the cumulative percentage of the number of California households that use domestic wells for their water source. You can see that in the inland valleys, more than 50% typical, and then along the coastal regions, it really varies from north to south. So when we use groundwater as a supply for a water system, we can tap into that groundwater in different ways, right? Depending on how far down we drill, depending on the subsurface geology, and depending on the way the aquifer is laid out. So you can see here in this schematic cross-section of an aquifer, we've got terminology that are used for different types of wells. So we have An artesian well, which would be the first one you could see on the right, where that well is being drilled down past the first aquifer through a confining unit, which might be something like clay or a rock layer, and then it goes further down into a confined aquifer, which is typically of higher quality and usually a preferred water source if available. So that artesian well would draw from that lower confined aquifer. A water table well, on the other hand, would draw water from the unconfined aquifer. And unconfined aquifers are used in many cases, but in some situations they may be lower quality because they're more impacted from surface sources of surface contamination. We can also have some water table wells that are referred to as perched water tables. So if there's like a small confining unit that accumulates a bit of water above it, but is not part of the main aquifer, that would be a perched water table well. We also have what's called a flowing artesian well. So this is a well that if you drill down into a confined aquifer, the pressure might be such that the water just flows naturally out of the well without having to use a pump. So it can be extracted using the forces of gravity and pressure. The way that happens is that we have a recharge area. As you can see in the upper left, there would be an area where when it rains or snowmelt would infiltrate into the soil and enter that confining aquifer, which may have a higher level than the unconfined aquifer, as you can see in the figure. And so that higher water table creates a higher potential energy based on the potentiometric surface, as you can see in the dotted line, and that will create the pressure that causes artesian wells to flow without having to use a pump. All right, so when we describe groundwater sources, we can use this kind of terminology: the recharge area, confined aquifer, unconfined aquifer, perched aquifer, ground surface, etc. These are some of the terminology that we use. Well construction. So when we tap into a groundwater source, we're usually installing a well with a screen and in some cases a pump. So how much water can be stored in an aquifer has to do with the void spaces in the underground sand or gravel. And so typical construction of a well would look like what you see in the figures over to the right, where we've got the well drilled down to a certain extent, and then you have an area of the well that's screened. The screened area is what takes in water, so the rest of it is not permeable, but the screens are where the water comes in through that portion and is pumped up to the surface and into the distribution system using a pump, either vertical turbine or submersible pump. When that happens, you get what's known as a drawdown of the water table, which we're going to talk about in more detail in a second. So that's going to bring down the level of groundwater at that location while the pump is turned on. When the pump turns off, the level of groundwater will come back up to its original elevation. So groundwater flows towards the well, it enters the casing through the screen, where it's then lifted up by the pump and discharged to a distribution system. Wells are constructed usually using drilling methods like hydraulic rotary drilling, or in some cases other methods depending on the subsurface conditions. The borehole is advanced using a rotating bit that's attached to a pipe and held up with a drill rig mast, as you can see here in the figure. The cuttings from the drilling are removed by circulating a drilling fluid, which is usually some kind of clay mixture like bentonite clay, to provide the viscosity necessary to bring up those cuttings back to the surface and continue excavating deeper and deeper into the well. All right, so that process is carried out until the water table is reached, and at the same time a pipe casing is typically installed. So in terms of aquifer storage and groundwater banking, we would consider this aquifer as being sort of analogous to a tank, right? So it's a very large underground tank that can be used to store water during times of low demand, and then extract water during times of high demand. So if you can imagine that we have native groundwater here in a confined aquifer, and during high demands we're extracting water out of that confined aquifer. But then when the demand is lower, like let's say during winter months or during wet periods, we can inject water back in, whether it's water from runoff or treated wastewater. We can inject it back into this aquifer and store water in the zone that you can see here called stored water zone, right? So that later, when it's a higher demand again, we can then extract water without continuously drawing down the level of reserves in this aquifer. So this type of process of managing an aquifer has been used in California successfully to create a more sustainable approach to extracting groundwater. So this is a graph showing a case study of Santa Clara Valley Water District that is heavily reliant on groundwater. And you can see starting right after in the early 1900s, the natural groundwater level was at an elevation of approximately 100 feet. Over the first 50 years or so that the groundwater was extracted, it decreased to as low as negative 100 feet from its original position. So 200-foot drop in the elevation of that aquifer. And that's where, because of the declining levels in the aquifer, the district started importing water for the first time. And you can see that that has led to the recovery of the aquifer. So increased in the 1980s, 1990s or so, increased deliveries of imported water from federal water sources. You can see the water table has now gotten back up to more or less the level it used to be in the early 1900s. So this is one example of some of the strategies that can be used to maintain consistent levels of water in an aquifer. Another really good example of this is the Orange County Water District. So Orange County lies over a very large aquifer, which is divided into a couple different zones. So we have the deep aquifer, we've got the principal aquifer, and then a shallower aquifer. And there's different confining layers in between that separate out different levels of this aquifer. But in general, the principal aquifer is used to supply water for much of Orange County. And the aquifer is recharged in part by the Santa Ana River, where the water district has constructed several recharge basins. So basically large basins where the water from the river is diverted into these basins and it's allowed to percolate down into the aquifer again to recharge the levels. In addition to that, there is treated wastewater that comes from wastewater treatment plants in Orange County. That treated wastewater is then injected back into the aquifer again to maintain the levels of water stored in the aquifer, and also some injection wells are used to prevent the intrusion of salt water from the Pacific Ocean in order to keep the quality of water at a level that's suitable for drinking purposes. So here's another good example of a managed aquifer that has maintained its supply without drawing down too much on the reserves. So again, when we estimate or calculate how much water is available in an aquifer and how quickly we can pump it out of the aquifer, this all has to do with the porosity of the soil. So groundwater originates from infiltration, right? When it rains, when there's stream flow, we have lakes and reservoirs, we have snow melt, that water will some of it will infiltrate through the soil and into the aquifer. So as the water percolates downward, you have thin layers that are left behind. They coat the soil grains, giving the soil some kind of moisture, and eventually you reach a saturated zone where the pores are essentially completely filled with water, and that's what we would refer to as the water table. So the transition from that moist soil into the completely saturated zone is what we refer to as the water table. So stage 1, we have moisture barely coating the particle. Stage 2, moisture collects at the particle contacts. And then stage 3 is where the entire void space is filled. The soil porosity, N, is defined as the void volume divided by the total volume. So we can have, for different soil types like sand and gravel, sandstone, shale, or limestone, we have some values that can be used as like typical porosity values for these soil types that you can see here on the bottom right. Soil permeability is defined as the ability of the soil to transmit water. So the more permeable a soil, the easier the water will flow through it. We define soil permeability using a coefficient, K, which is based on Darcy's law, which states that the velocity of flow is directly proportional to the hydraulic gradient. So if the velocity is represented by V and K is the coefficient of permeability, I here is the hydraulic gradient, you can see that we have the equation V equals K multiplied by I. And for gravel, we can use a value of K equal to 1 foot per second. For fine grained soils, we could use a K value of 10 to the negative fifth feet per second. So again, that water moves through the aquifer, moves through at a different speed relative to the type of soil in the ground, in the aquifer, in the ground. And as it comes in through the screen and gets pumped out into the distribution system, the pumping action draws down the level of the water table. As you can see here in the graph to the right, which shows the drawdown cone, and the extent of drawdown is based on how quickly water is pumped out of the well. So this drawdown distance, or the drawdown cone, we don't want to let it reach as far down as the well screen, of course, because then you're going to start to suck in air through the pump, which is going to create some problems with extraction of groundwater. So it's important to be able to calculate the production rate of a well and its pump, so that we don't draw down the level too far. Pumping water causes drawdown. Steady state, if we assume steady state radial flow to a well, assuming the aquifer is ideal, homogeneous characteristics, it's defined in that situation as by having uniform withdrawal rates, a stable drawdown curve, and horizontal laminar groundwater flow. So this is not necessarily always the case in practice, but if we start with these assumptions, we can start to put together the model that is used for estimating production rates for a groundwater well. And that's where this equation comes from, that kind of theoretical basis. So if those ideal conditions are true, assuming those ideal conditions are at least partially true, the well discharge rate can be estimated using the equation shown below. So Q is equal to pi times K, which is the coefficient of permeability. And then we have the variables H1 and H2, as well as R1 and R2. So R1 is referring to the distance between the well and some observation well. R2 is referring to the distance between the well and a second observation well. So at the first and second observation well, we would see that the level of groundwater will be lower than it is at the static level. So you could see H2 is smaller than the distance which is labeled static head, the static water level, and H1 is even lower than H2. Then we will have the water level in the test well while we're pumping. So if we're pumping at a constant rate Q, we should see the shape of the groundwater something like this, and we can measure those drawdowns in observation wells. So as long as we have 2 observation wells, we can use the equation shown here to calculate the flow rate that's possible for a given drawdown level. So that first case, this is for an unconfined aquifer. Now if we have a situation where the aquifer is confined, like we have an impermeable layer, and that's separating the unconfined aquifer from a confined aquifer, and say we drill a well that extends into the confined aquifer, and we start to draw down water from that confined aquifer. The flow rate that's produced from that well would be calculated using the formula shown here, which is very similar to the one you saw on the previous slide. All right, so Q is equal to 2 pi times K times B multiplied by this factor of the H0 and HW and R0 and RW. So in this case, R0 is the distance from the well to the point where the drawdown starts, and RW would be the radius of the well itself. All right, so in general here for these two equations, you can see that R would be the radial distance away from the well to some point where we're measuring the drawdown, and H would be the height from the impermeable layer up to the level of drawdown. All right, the difference for a confined aquifer is that we also have this depth B, which would be the thickness of the aquifer, the thickness of the confined layer. So taking all that information into account, again, we can calculate the potential production of this well given its characteristics. So let's do an example problem. A 2-foot diameter well is drilled into a confined aquifer which has a thickness of 50 feet, and it's overlain by an impermeable layer that is 115 feet. For a pump test, we find that the initial piezometer was 49 feet below the ground. The water was then pumped out at a flow rate of 0.46 cubic feet per second for several days, after which the water level stabilized with the following drawdown readings. So at the test well site, the drawdown was 21 feet. The first observational well, which was 30 feet away from the test well, had a drawdown of 12.1 feet. And the second observation well, which is located 100 feet away from the test well, had a drawdown of 7.9 feet. So the question here is, what is the permeability of this aquifer? And then the second part, using that permeability, what is the maximum well discharge if the drawdown of the well is lowered all the way down to the top of the confined aquifer? All right, so for this one, we have a 2-foot diameter well, and it's drilled into a confined aquifer. Which has a thickness of 50 feet. The impermeable layer is 115 feet below surface level. So let's say we have our surface here. Here's our well. So we've got our screen area here. And let's say that this is our confined aquifer. All right, so the thickness of this confined aquifer, we're told, is 50 feet. Got some kind of confining layer here. The depth to this confining layer is 115 feet below surface. So we're interested in doing a pump test. For the pump test, we're pumping out of this well at a flow rate of 0.46 cubic feet per second. And after several days, the water levels stabilize with the following observed drawdowns. So within the test well, we started off with the initial level of water being at a depth of 49 feet. And after pumping the water out for several days at 0.46 cubic feet per second, the test well drawdown was 21 feet. Alright, so this initial drawdown here was 21 feet. Let's say we have some observation wells. So we're told we have 2 observation wells. One which is located at 30 feet and another located at 100 feet. Alright, so we have the drawdown here, which is at a distance of 100 feet. The drawdown is 7.9 feet at observation well number 2. At the first observation well, we've got a drawdown of 12.1 feet, and that distance is 30 feet away from the test well. So, with that information, we are asked to find the permeability of the aquifer, and then given that permeability, we're asked to find the maximum flow rate. Now the maximum flow rate would occur under a scenario where we pump even more out of this well to draw all the way down to the bottom here, the maximum level. So we would have a drawdown curve that looks something like this under the maximum flow rate conditions. And so this is a 2-part problem. In order to find the flow rate for these maximum conditions, we need to know what the permeability is. In order to find what the permeability is, we do a test with a lower flow rate, and we look at the drawdown levels in 2 observation wells, and we can calculate K. So we're going to apply the equation that we have for a confined aquifer, which is that Q is equal to 2 pi times K times B times the ratio of H0 minus HW divided by the natural log of R0 divided by RW. Now that's for the maximum drawdown. For our test well drawdown, we would just change this equation so that we have H2 and H1, R2 and R1. So first we're going to apply this version of the equation with our 2 observation wells to calculate K, and then we're going to use that K value in the second equation using H0 and HW. Alright, so let's make some space here. Alright, so I'll put that dimension over here. Let's not forget that our distance here is 115 feet. So before we start the drawdown, the depth to the groundwater level in the test well is equal to 115 feet minus 49. We can call that H sub 0. H sub 0 equals 115 minus 49, which is equal to 66 feet. So the next distance that we want to find is H1 and H2. So H1 would be the distance from the bottom here up until that drawdown point. H1. H2 would be up till the distance here, our second observation well, the drawdown point. So H1 therefore is equal to 66 minus 12.1, which is equal to 53.9. H2 is equal to 66 minus 7.9, which is equal to 58.1. Finally, we've got HW, which has a drawdown of 21 feet, so it's equal to 66 minus 21, which is 45 feet. Alright, so if we substitute into this equation, we know here 50 feet is equal to B. If we substitute in this equation and we solve for K, we'll find that K is equal to 0.46 cubic feet per second divided by 2 pi times 50 feet. 50 feet is the value of B. And that multiplied by 58.1, which is H2, minus 53.9. So that has the units also of feet, and 53.9 is from H1, so H2 minus H1. If we multiply feet by feet, we get feet squared. Up here we have cubic feet per second, so this gives us a value of feet per second. We're going to multiply that by the natural log of R2 over R1, where R2 is equal to 100 feet, R1 is equal to 30 feet, so it's natural log of 100 divided by 30. So this whole thing right here equals 0.00042 feet per second. Again, feet per second because the 2 of the feet cancel out here. We're left with the units feet per second. So 0.0042 feet per second is the permeability coefficient, K. The second part of this problem is we're going to apply that permeability coefficient to determine the maximum drawdown. So here, instead of H1 and H2, R1 and R2, we're going to use H0 and HW, R0 and RW. So H0, we've already determined here, is equal to 66 feet. And HW, in our experiment, HW was the distance from the bottom up until this drawdown of 21 feet, which we determined was 45 feet. However, under our scenario where we have a maximum, drawdown, which goes all the way down to the bottom, this HW is essentially equal to 0. Right, so HW under our first test case was equal to 45 feet. However, under the max for the Q max, this is when we draw all the way down to the bottom, HW equals 0. Okay, so that leaves us with 2 times pi times K. K is equal to 0.00042 feet per second times B, which is equal to 50 feet. Multiplied by H0 minus HW, so 66 feet minus 0. Divided by the natural log of R0 divided by RW. R0 is assumed to be 700 feet. RW is equal to 1 foot. So this gives a maximum flow rate of 1.3 cubic feet per second.